Well, hello friends. Welcome back to the program. Today we are going to continue working on the Serenity OS kernel heap allocator. And this is the third video in a series about that. And the goal, of course, as I stated in the first one, is to get to a point where I feel like we can remove this old comment here saying that the kernel heap allocator is really quick and dirty. And I think we're probably going to do that today. There's one big thing I want to do first, though, which is to get rid of the so-called eternal heap. So the eternal heap is a kind of a premature optimization in our kernel. So we have this thing called kmalloc eternal, and it's a variant of kmalloc that you can call. And the difference between kmalloc eternal and regular kmalloc is that there is no corresponding k-free eternal, because these things are expected to live forever, right? That's why the name. So the idea with this concept was that in the kernel, we have a number of objects that we know for sure we're never going to free. So early on, I was thinking, hey, if we're never going to free these, why don't we just bump allocate them out of a static buffer? That way, there's no risk of fragmentation, right? So we know that they will be perfectly packed within that area of memory. It's almost as if you had them in the ELF data segment. But since you only know that you want them at runtime, they still get that property of being like really densely packed in memory. But if we look at the kernel memory stats, we can see that there's 256K basically of memory allocated in this way. And that's not that much, especially considering our eternal range reservation is 4 megabytes. So we are putting aside 4 megabytes of kernel memory, and then we're allocating 256K out of it. This is just very wasteful, and I don't really think that the optimization makes that much sense to begin with. And even if it did, optimizations should come from a place of data, not from a place of hunch and intuition, right? And I have absolutely no data to say that this thing is valuable, but here is a piece of data that says that it's using a lot of memory unnecessarily, because we're wasting 3.75 megs effectively on this thing. So I think let's just get rid of it and see if everything works fine without it. And then in the future, if we want to come up with something to replace it, because we have some data that suggests that this is a real performance problem, then we can come back to that. But as the original author of kmalloc eternal, I can tell you that it was not a data-driven optimization. It was just something I did early on without much thinking. So let's see. So the way that we inject kmalloc eternal as an allocator for various objects is that we have a macro. So we have make eternal, and it's a simple macro that just injects operator new and operator delete into a class. So operator new calls kmalloc eternal, and the operator delete will simply panic if it gets called, because as I mentioned, these things are not supposed to be deleted. But I think what we're going to do is we're just going to just straight up get rid of it. And this will be a little bit of a riveting text editing right here. Just nuking this from every occurrence that we have of this macro. Not terribly many. And it's only used in the kernel. In user space, and actually in the kernel also, I think we have this other thing called never destroyed, which is a bit more of I guess, a bit more sophisticated solution to the same idea. But Never Destroyed puts its storage into the ELF data segment instead of using a dedicated heap. Let's see, make eternal. Can I? How do I jump to the next thing? Surely there is like keyboard shortcuts for this. Maybe, well, I'm sure that somebody will tell me in a comment what the appropriate shortcut is for like jump to next find result. What might that be? Find next occurrence. Okay, so Control G. Maybe that's within this buffer. Find highlight usages. Next highlighted usage. No. Yeah, I don't know. I don't know what the keybind for that would be. Guess we're doing it the old-fashioned way here. Not the end of the world. We don't have that many. And yeah, so I think once we get rid of this eternal heap, and everybody is just allocating through kmalloc, then really the main thing I want to add at that point is like a couple of little safety checks that we missed in the last two videos, and then maybe we would be good to remove that comment and say that maybe this is not so quick and dirty anymore. Yeah, I guess we can let that build in the background while we go and also prune the rest of this stuff. So all the eternal related stuff just goes away. Eternal range size, bye-bye. Oh, this is really nice. This is really quite nice. Eternal. Okay, so here is this the only instance of actually calling kmalloc eternal? So this is an array of kernel symbol pointers that we store all of the loaded kernel symbols in. Let's just put that in kmalloc memory. That's not the end of the world. And this comment, we intentionally leaked the reference to serial device here, as it is eternal. We'll just put a dot. Or a period. Okay, and then I'm eternally grateful for all the love and support this project gets from the second happy birthday post. That is still very much true. I am so incredibly grateful for all the love and support for Serenity OS. This is just a fantastic journey to be on, and it's funny that we get reminded of that at this moment, but so it's always a good time to mention that. And I'm just crazy grateful to be doing this still and with all of you. Super fun. Okay, so we got a little bit jumbled there, editing the code while it was building, so hopefully now that would just work. I'm hopeful that it will just run. I guess since I edited some ACK file, we get to eat one big rebuild. But assuming that this all works out, we can just start working on the commit message right away. And then we had some Clang format fix-ups, but that's kind of neat. So if you try to commit and you have style mistakes, then if you just git commit -a after that, then the Clang format edits will be in place at that point, and you can just kind of commit again, and it will work out. Kernel. remove the kmalloc eternal heap. This was a premature optimization from the early days of Serenity OS. Eternal heap was a statically allocated, was a simple bump pointer allocator over a static byte array. We would reserve 4 MIBs at boot, and only ended up using 256 kilobytes, wasting the rest. My original idea was to avoid heap fragmentation and improve data locality. But both ideas were rooted in cargo culting, not data. Yeah, this patch replaces all kmalloc eternal usage by regular kmalloc. Yeah, hopefully that would just work. We'll find out when it finishes building. So we're like halfway through the build. And then some other stuff I'd like to do. I mentioned some safety checks, right? So I was thinking when we k-free something, k-free sized as it's called now, then we can do a bit more validation that the pointer we're freeing is actually within the virtual range of the kmalloc allocator. So let's see, for slab heap, deallocate. Yeah, so when you're deallocating a slab, which we worked on last time, we just locate a slab heap with the corresponding size, and then we dereference the base block of that slab, but we don't actually verify first that the slab is within this slab heap. So what we can do here, we can't check that it's within the slab heap without visiting every block, which would run in linear time. But what we could do is we could add a verify that it's within the virtual range of the entire kmalloc heap, which is actually two-parted. So there are two virtual ranges. There's the initial kmalloc heap, which is what's it called? The pool. Maybe we should rename this. Actually, let's rename that first of all. Because I want to call that initial kmalloc initial memory or something like that. Initial kmalloc memory. And instead of pool size, we'll call it initial. Actually, let's make this const expr size t initial kmalloc memory size is going to be 2 megs. That sounds vaguely reasonable. And then why is this all the way down here? That seems unnecessary. So maybe we can yoink that up to here so it's next to the size. Okay. Yeah, there we go. Initial kmalloc memory. Yeah, so there are two virtual ranges to know about. Is the initial range, which is statically allocated in the kernel image itself in BSS. And I think actually it's after BSS technically, but it's part of the image. So we have a 2 megabyte static buffer that we create the initial allocator on top of. And after that, we also make a range of VM that we allocate out of dynamically. So we need to check both of those ranges. So I guess, well, first let's do this little change right here. So that worked out. It built, I mean, let's see that it runs. Hopefully it does. And then this is a simple naming change, just renaming kmalloc pool heap to initial kmalloc memory. Yeah, and it runs, and we're up and running. We have no eternal heap anymore, which means that we don't have that 256K entry here. Instead, we have an additional 4 megabytes available, no longer occupied by that kernel buffer. So that's pretty cool. All right, that seems good. So wait, did I like that name? Initial kmalloc memory? I guess that's okay. Initial kmalloc memory size. Yeah. Let's commit that kernel. Rename kmalloc pool heap initial kmalloc memory. Okay, so in order to check if an address is a valid kmalloc address, we have to check two things. We have to check that initial address. So we can make a helper here. So actually the helper can't be static because the virtual range is stored further down. Where's the virtual range? Here. Right. So bool is valid kmalloc pointer. And then here we would just put an address, putter. Okay. So if putter is greater than or equal to kmalloc initial kmalloc memory, and putter is less than initial kmalloc memory plus initial kmalloc memory size, then return true. And also, if we have a virtual range, so if expansion data has value, if it doesn't have value, we're not set up for expansion yet. Otherwise, if putter expansion data virtual range dot base as putter. Yeah, so same idea as the other one. Expansion data virtual range end as putter. Oh, I guess actually we even have a contains helper. Yeah, we should just use the contains helper. And maybe this would be even more descriptive, or yeah, this seems a bit nicer. All right. So how are we going to use this API? Well, when you try to deallocate something, we can check it out right here. So verify kmalloc. I guess actually we have to do it after we take the lock, but we can do it right down here. Verify g kmalloc global is valid kmalloc address. Now I'm thinking we should just bake that into deallocate itself. Yeah, we'll do it here. Okay, what did we do wrong? Okay, well, I guess I forgot a semicolon somewhere. Ugh. Oh, it's right here. It was a forgotten right paren. All right. Yes, that's exactly what I want to do. I just want to verify that it's a valid kmalloc address. So that if you try to deallocate something that didn't come from kmalloc, this is sort of it can have this thing would have false positives, right? Because it might be a part of the VM that we didn't start handing out yet, but it does not have false negatives because it's completely inclusive of all the possible kmalloc addresses that we could ever hand out. And the idea, of course, here is simply to catch bugs instead of just letting them slip through the cracks. Yeah, so I think that's a good one. Verify that k-free sized look valid. Let's do some simple pointer arithmetic to verify that the address being freed is at least within one of the two valid kmalloc VM ranges. Yeah, that's a really cheap check, just comparing some pointers. Okay, and then, I wanted to improve scrubbing as well. So currently the way scrubbing works, scrubbing is when you make an allocation, we will give you scrubbed out data. So it's all initialized with a byte pattern. And likewise, when you free something, we will scrub it with a byte pattern before putting it back into the free list. And the idea is simply to avoid having old, potentially secret data lying around. Which we talked about in the last video. But the way scrubbing currently works is that it happens in two places. So we have this heap template thing. This is the original generic allocator, and it performs scrubbing after finding the suitable allocation slot. And likewise, free scrubbing is performed when freeing. Although, now I wonder, I was thinking like we could move this out and perform this further out. But that also makes me realize that if you kmalloc, say, 10 bytes, what we actually do is we find maybe a 16 byte chunk and give that to you, or even a 32 byte chunk and give that to you. And we want to scrub out the entire 32 bytes that we're giving you, even though you only ask for 10. And my original train of thought here was to scrub at the outermost layer, so in kmalloc and in k-free sized. But then I just realized that if we do that, at that point, we don't have the information of the actual allocation size. And I guess we could plumb that out if we make an API for it, but I don't know. That seems like a strange contortion to make just in order to scrub here instead of in the allocator. So maybe that's okay. Yeah, maybe it's all okay. All right, so I think here we're just gonna get rid of this comment now because I feel okay about this allocator finally. I'm definitely gonna keep working on it, but I think I can nuke that comment with a clean conscience. And I wanted to do it in a video since I started talking about doing it in a video. So let's do that. Remove ancient, remove old comment about kmalloc being quick and dirty. We've finally gotten kmalloc to a point where it feels decent. There's decent enough to drop this comment. There's still a lot of room for improvement, and continue working on it. Yeah, that's really it. Oh man, that is possibly the most satisfying fix me. And I guess it wasn't even a fix me. It was just an old funny comment. And in a way, it's a little bit sad to see it go, but at the same time, it's also really nice to finally feel like I've done okay by kmalloc. I am going to continue improving it. I have a bunch of ideas to make large allocations faster and to make better use of the VM range. We can do much more sophisticated allocations, and we do a bunch of wasteful things with block alignment and so on. So tons of stuff to do, but I think this will be it for today's video. This is a bit of a shorter one. I'm really happy with the progress that we've made on this. And if you made it this far in the video, then I thank you for watching and hope that you've seen something interesting in this series. I've certainly had a good time just hacking on this, and it's really lovely to see how many people have a genuine interest in seeing like something as esoteric as a kernel heap allocator get changed around. So that's awesome. Thank you all very much for hanging out, and I will see you all next time. Bye.